Hi class. Today we're going to be looking at measures of variance for this week's material, primarily the range, variance itself, and then standard deviation. So let's take a look. So the first thing we want to look at is dispersion. Dispersion is kind of another way of talking about variance. It's just how much is the data distributed around the mean. I've got an example here with 3 different data sets. All essentially normal in their distribution, which would put the mean right in the middle, right? If you think about what we learned about central tendencies the other week is that for normal distributions, you know that the mean, median, the mode are all going to be the same value. Anyways, for this week's stuff, you can tell looking at each distribution that they're dispersed differently, right? The plot for A has a much tighter distribution and the plot for C is much looser. And what that means is we're looking at, like, on average, how much does the data in our distribution vary from the mean? And the values in A are much closer to the mean than the values in C. And so we're going to kind of be looking at these types of things in this video. So the first measure of variance is range. And for this, you literally just take the lowest value in your data set and the highest value and subtract them. So for example, if you had a list of data and let's say your lowest value was 5 and let's say your highest value happened to be 100, then your range would just be 100 minus 5, which would be a range of 95. And that might be, a useful a statistic for whatever it is that you're trying to look at. But the other thing is the range has some issues. One of its biggest problems is that it's very susceptible to outlying values. For example, let's say that you have a positively skewed distribution. So you have a distribution with a bump over here and then a really long tail on the positive side, right? What that's going to do, well, first of all, these numbers over here are going to pull. Right, the mean, we would want it to be here, but those things are going to pull the mean this way, right? That's why it's a skewed distribution. So it has that problem to begin with. The other thing that we want to look at is if this is 5 and this is 100 out here, this isn't going to give me a very good read as to how well my data is distributed, because really the bulk of the data is here, right? You can see that, if this is a frequency plot, this is frequency versus whatever it is I'm plotting, right? The bulk of my data is sitting right here. But this thing is going to give me a huge range. So it's a little misleading. So what we do instead is we're going to use the interquartile range as one way to kind of get around some of the weaknesses of the range. And so the interquartile range just says, look, what's the range of the middle 50% of the data? And so what you would do to find that is, you line up all of your things. You know that the median, there's the value right in the middle. That's the 50th percentile. And so then the middle of that is the 25th percentile, and then the middle of this other side is the 75th percentile. And the interquartile range looks at the values between the 25th and the 75th percentile, right? What are those values between the 25th and the 75th percentile? And depending on what numbers are actually in here, that's going to change what that interquartile range is. And sometimes you'll see that as interquartile range. So if you ever see IQR, that's what it's talking about, the interquartile range. And you find it by first finding the median and then looking at the back 50% and it's like finding the median of that, and then looking at the top 50% and finding the median of that. That'll give you the 25th and the 75th percentile. And this will be helpful for us when we look at the box and whisker plots at the very end. So next thing, so range, kind of a weak measure of variance, but it's often used. Interquartile range is a little bit better because you can cut those outliers out. But again, it isn't perfect. The next one we want to look at is variance itself. So a couple of different ways to talk about this. First is there's sample variance, which is often symbolized by s squared. And you know, your technical definition of this is going to be, it's the sum of the squared deviations around the mean divided by n minus 1, whatever that means. We can write that out in equation form. You see here on the right. And then there's population variance, which is sigma squared. Now this one you need to be careful of because you very rarely ever calculate population variance, right? Normally you're studying populations that are much, much too large for you to get data from everyone. That's why we take samples, because we're trying to estimate what the variance of the actual population is using a sample. So I have some fake data here that we can kind of play around with. I made up some numbers. I'm calling it hours of sleep. Yes, I see that there's an 18 in there. Maybe somebody in your sample happened to be sick and slept for 18 hours the day that you surveyed them. It could happen. Anyways, so we have this data. We want to calculate the variance. And again, variance, we're looking at how much on average do our numbers vary from the mean. So the first thing we need to find is the mean. So as we're going through and doing calculations like this, right? So the sample mean is going to be the sum of all of the values divided by the total number of values. When you run the numbers for this, we're looking at 48 over 6 when you add all this stuff up, which gives me a mean of 8. And okay, so I've got the mean. Now I need to calculate how much each one of my data points varies from the mean. So I'm going to actually hop out to see if I can do this. Okay, never mind. I'm just going to do it right here. So what I want to look at is, next thing we want to calculate is this bit. What is the deviation from the mean for each of my numbers? Okay, so you start with, I'm going to have 6 minus 8, and then 7 minus 8, and 3 minus 8, and 4 minus 8, and 10 minus 8, and 18 minus 8. Okay, so I'm going to find out how much does every single number in my sample deviate from the mean. First one is -2, -1, -5, -4, then 2, then 10. Okay, so I have all of my deviations. Now, this is something that's really important to look at, and you'll see this. You'll see this all over the place. Questions asking, well, why is it so important that we square those deviations? And this is why. Because anytime you sum the deviations around the mean, right, this symbol stands for summation. So if I were to just add up all these deviations right now, I'd get, well, these two add together to give me positive 12. And then I've got -9, -10, -12. If I add those, it's summed to 0. And that'll happen every single time. If you take your deviations from the mean and sum them up, they'll add to 0 every single time. And they do that because that's kind of the definition of the mean. You found the average of all of the values. So if you sum up the differences of all of those values from the average, you're always going to get 0. And for us in this case, 0 is not a useful number. So we want to have an actual variance. So they square these differences because any number squared becomes positive. Okay, so if I look at each of these things, if I square them, I end up with 4, 1, 25, 16, 4, and 100. Okay, now that I found the difference, squared the difference, now I can sum everything. Okay, so I add up everything on my list, and this just happens to sum to 150. So we're almost done. I found the differences, I squared the differences, I've now summed the differences. The last thing we need to do is then divide by n minus 1, which is the number of values in my sample minus 1. So for us, this is going to be 7, because I have 1, 2, 3, 4, 5. Oh, hold up. I have 6. Oh, this is going to be 5. Okay, so divide by 5. So 150 divided by 5 gives me 30. And that is my variance for this data set. Now, a couple of things I want to point out here is how, looking at this number, how useful is it? And I think it's important to kind of consider this, because if you look at what you have to think of this in terms of the units, okay? We're looking at hours of sleep. So this is 6 hours of sleep. This is an average of 8 hours of sleep. So this number is still in hours of sleep, but then I squared it. So now I have squared hours of sleep. And then I did a sum and I did a little division. But down here, I'm still looking at my hours of sleep. My unit on here is squared. And it doesn't really make a whole lot of sense to look at this in terms of squared hours of sleep. Nobody talks about that. That's not a useful unit. There are some statistical tests like ANOVAs where you're doing analysis of the variances. But normally for us, the variance isn't a very helpful or useful unit because of the squared nature of the unit there. So we're going to do one more thing to this and kind of land with the measure of variance of choice, which is standard deviation. But the last thing I wanted to talk about on this slide here is going back and then looking at this n minus 1. Okay. Why n minus 1? If we're looking at an average, shouldn't we just, like we did over here, divide by n? Why are we dividing by n minus 1? So why divide by 5 instead of dividing by 6? And the reason is because we're dealing with a sample. If we had every value in the population, then we would just divide by n and we'd be fine. But because we're dealing with a sample, and all samples are full of bias, this n minus 1 is a way for me to adjust for the bias a little bit. We'll see in later chapters why this is so meaningful, because we're going to be using this statistic to make some inferences, and this keeps my inferences more reasonable. So we use the n minus 1, and again I'll talk about that later. But you use the n minus 1 where you're dealing with a sample. If you ever see this written as just divided by n, then that's looking at the population and not the sample. Okay, that's the difference between those two values. Okay, so we're sitting here, we're looking at, we just found our variance to be 30, right? And now we want to take this one step further and find the standard deviation. And again, the reason why we're finding the standard deviation goes back to that idea of units. And before, when we found the variance, right? When we found the variance is symbol s squared is 30, and then I had hours of sleep squared, right? This is not a very useful unit for us, so we're going to avoid using that. And we do that by taking the square root. The square root undoes this square. It brings me back to the original units of the study, which are hours of sleep. And now I have something that I can talk about. So for this data set, right, we just calculated the variance to be 30. So the standard deviation is just going to be the square root of 30, which is... Get my calculator out here and take the square root. 5.477. And then now my final unit is hours of... I'm back to hours of sleep. Okay. So and again, I'm using this n-1, so this is a standard deviation of a sample, okay? We'll look a little bit later at what we call the thing that, if we're trying to estimate the standard deviation of a population. But this is the standard deviation of our sample, 5.477 hours of sleep. And what this is really telling us is this says that on average, these numbers over here vary from the mean of the data set by 5.477 hours on average, right? Now, we know that our mean is 8. And so if you look, right, each individual number, right, this one only varies from the mean by 2. This one varies from the mean by -2. This one varies from the mean by 10. Right, so each number in the data set varies from the mean differently, but on average, the amount that they vary from the mean is 5.477 hours of sleep. Okay, that's what the standard deviation is telling us. That's what it's talking about. It's giving us an average amount of deviation of every single number in the data set from the average of the data set, or the sample, whatever it is that we're looking at. Some of the really cool things that the standard deviation does. So here I have a plot. This is a normal distribution. That's important. When the distribution is normal, and I talked a little bit about last week why normal distributions are so cool. This is the main reason why. When your distribution is normal, you can apply this really cool rule that if you know what the standard deviation is, so here's the mean, right? And this is saying, all right, here's the mean. Here's one standard deviation to the right of the mean. Here's one standard deviation to the left of the mean. So if I kind of look at this, if I know that my values are within one standard deviation of the mean, plus or minus, I know, if the distribution is normal, that I'm looking at 68.2% of all of the values in the entire distribution. If I hop out and say, okay, let's look between two standard deviations, okay, this ups my percentage. So let's see here. 13 and 13 is 26. And then the 0.6, so this is going to be 27.2. So 68.2 plus 27.2. You see, I'm just kind of adding these regions. 68.2 plus 27.2. So this brings my total up. If I'm within two standard deviations of the mean, then, right, so between here and here, well, now I'm looking at 95% of all of the data in the sample, okay? So if you know what the standard deviation is, and if you know, this gives you a really good idea of what the distribution looks like and how spread out all these values are within your distribution. And so, but this idea of like looking at these percentages, we're going to talk a lot about next week. So just a little bit of a spoiler for stuff that's coming. Another way to kind of think about standard deviation is to look at a visual. So I have 4 different graphs here. Each of these distributions is normal. The green one happens to have a different mean than the others, right? So you can see these are the averages. So this green distribution is centered around -2, and the other ones are centered around 0 for whatever reason. But they all have different standard deviations, okay? And just by looking at these, we can tell which one has the highest deviation, okay? If I look at the orange distribution, look how wide it is. It's really wide, it's really flat. My values are very, very spread out around the mean, right? This would have a really high standard deviation. On the other hand, the blue one, this is really tall and really skinny, okay? The standard deviation from this one, so this orange one is high standard deviation, the blue one has a low standard deviation. And so this kind of like, if you want your average to be a really good representation of the sample, then you want a low standard deviation. Because a low standard deviation means that all the other numbers, like this blue one, all the other numbers are pretty close to the average. But if you're trying to use an average to describe a distribution with a high standard deviation, look at this orange graph. Okay, these values out here, they're really far away from the mean. The mean, right? The average for this distribution, this would be a terrible descriptor of these values over here. Whereas with this one, the blue distribution, the average is a much better descriptor of the bulk of the data. So there could be some cases where a high standard deviation would be good, where you don't want everyone to be clustered up in one little group. You want your study to be spread out. So every study that you're looking at, there are different, right? It's just different. Sometimes you want, and I think that in general, most studies are trying to get a tight sample. They want low standard deviations. But there could be some cases, depending on what you're studying, where you want the standard deviation to be high. Last thing that I wanted to look at is the Box-and-whisker plots. And this kind of goes back to the range and the interquartile range stuff. But they look like this. They are just a representation of the name that they were given, right? You have the box and you have the whiskers, right? So how do you make a box-and-whisker plot? Take your data. So here's, you have some massive data set. First thing you do is find the median. Okay. What's that number that's in the middle? Okay. That's this thing. The next thing you do is you say, okay, what number is at this end of my distribution? That's going to be this value. What's the lowest number in my distribution? That's this value. Then to define your box, you need the 25th and 75th percentile. So just like we talked about before, now you're going to go back to this data and you're going to say, okay, where's the median here? Where's the median here, right? What number is in the middle of this 50%? What number is in the middle of this 50%? And those numbers are going to come out here. So this is the 50th percentile. This value is the 25th percentile. And this value is the 75th percentile. Okay? And from here to here is the interquartile range. So the Box-and-whisker plot does a really great job of kind of showing you how spread out the data is. And you can see that here's the bulk 50% of the data. You might have some outliers. Sometimes the way you determine an outlier is they say, okay, in order to figure out if a value is an outlier or not, well, the first thing you need to find is what's the interquartile range. Okay, figure this thing out because that describes, the middle 50% of your data. And then they say, okay, let's say your interquartile range happens to be 20. So then what they're going to do is they're going to say, okay, let's take 20 and let's multiply that by 1.5. And in this case, that's going to give you a value of 30. And they're going to say, okay, from here, from this back end of my box plot, from the 75th percentile, I'm going to add 30 to this value, plus 30. And this is going to give you some number. And whatever that number is, they force that to be this end. And then any data points beyond that, you would call outliers. Then they do the same thing here. They take this, they subtract 30 instead of add, and they make that value this end here. And then any data points beyond that, they would call outliers. They're saying that if any number is more than 1.5 times the interquartile range away from the 75th or the 25th percentile, those things we're going to consider outliers. That's not a hard and fast rule. Some studies, they may do 2 times the interquartile range, but normally they're using the interquartile range to kind of determine what's an outlier and what's not an outlier. Anyways, these are box-and-whisker plots. They're a really useful way of looking at data and kind of seeing how everything is spread out. And then if you have any questions about any of this stuff, let me know, and good luck this week. Thanks, everybody. Bye.